Okay. So let's look at a case study of an example where this one of the classic examples of deep reinforcement learning where this approach was applied. And so we're going to look at this problem that we saw earlier of playing Atari games, where our objective was to complete the game with the highest score. And remember, our state is going to be the raw pixel inputs of the game state, and we can take these actions of moving left, right, up, down, or whatever actions of the particular game. And our reward at each time step, we're going to get a reward of our score increase or decrease that we got at this time step. And so our cumulative total reward is this total reward that we'll usually see at the top of the screen. Okay, so the network that we're going to use for our Q function is going to look something like this, right? Where we have our Q network with weights theta. And then our input, our state S, is going to be our current game screen. And in practice, we're going to take a stack of the last 4 frames, so we have some history. And so we'll take these raw pixel values, we'll do some RGB to grayscale conversion, some downsampling, some cropping, so some pre-processing. And what we'll get out of this is this 84 by 84 by 4 stack of the last 4 frames. Okay, so the question is, are we saying here that our network is going to approximate our Q value function for different state action pairs? For example, 4 of these. Yeah, that's correct, and we'll talk about that in a few slides. Yeah, so it's more doing regression to our Q values. Okay, so we have our input to this network, and then on top of this, we're going to have a couple of familiar convolutional layers and a fully connected layer. So here we have 8 by 8 convolutions, and we have some 4 by 4 convolutions. Then we have a FC256 layer, so this is just a standard kind of network that you've seen before. And then finally, our last fully connected layer has a vector of outputs, which is corresponding to your Q value for each action, right, given the state that you've input. And so, for example, if you have 4 actions, then here we have this 4-dimensional output corresponding to Q of current S, as well as A1, and then A2, A3, and A4. Right, so this is going to be one scalar value for each of our actions. And then the number of actions that we have can vary between, for example, 4 to 18, depending on the Atari game. And one nice thing here is that using this network structure, a single feed-forward pass is able to compute the Q values for all functions from the current state. And so this is really efficient, right? So basically, we take our current state in, and then because we have this output of an action for our Q value for each action as our output layer, we're able to do one pass and get all of these values out. And then in order to train this, we're just going to use our loss function from before. Remember, we're trying to enforce this Bellman equation. And so on our forward pass, our loss function is going to, we're going to try and iteratively make our Q value close to our target value that it should have. And then our backward pass is just directly taking the gradient of this loss function that we have, and then taking a gradient step based on that. So one other thing that's used here that I want to mention is something called experience replay. And so this addresses a problem with just using the plain Q network that I've just described, which is that learning from batches of consecutive samples is bad. And so the reason because of this, right, is so for just playing the game, taking samples of state action rewards that we have and just taking consecutive samples of these and training with these, well, all of these samples are correlated. And so this leads to of inefficient learning, first of all. And also, because of this, our current Q network parameters, right, this determines the policy that we're going to follow. It determines our next samples that we're going to get, that we're going to use for training. And so this leads to problems where you can have bad feedback loops. So for example, if currently the maximizing actions that's going to take left, well, this is going to bias all of my upcoming training examples to be dominated by samples from the left-hand side. And so, so this is a problem, right? And so the way that we are going to address these problems is by using something called experience replay, where we're going to keep this replay memory table of transitions of state, state, action, reward, next state transitions that we have. And we're going to continuously update this table with new transitions that we're getting as game episodes are played, as we're getting more experience. Right? And so now what we can do is that we can now train our Q network on random mini batches of transitions from the replay memory, right? So instead of using consecutive samples, we're now going to sample across these transitions that we've accumulated, random samples of these, and this breaks all of these correlation problems that we had earlier. And then also as another side benefit is that each of these transitions can also contribute to potentially multiple weight updates, right? We're just sampling from this table, and so we could sample one multiple times. And so this is going to lead also to greater data efficiency. Okay, so let's put this all together and let's look at the full algorithm for deep Q learning with experience replay. So we're going to start off with initializing our replay memory to some capacity that we choose, n, and then we're also going to initialize our Q network just with our random weights or initial weights. And then we're going to play m episodes or full games. Right? This is going to be our training episodes. And then what we're going to do is we're going to initialize our state using the starting game screen pixels at the beginning of each episode. And remember, we go through the pre-processing step to get to our actual input state. And then for each time step of the game that we're currently playing, we're going to, with a small probability, select a random action. So one thing that's important in these algorithms is to have sufficient exploration. So we want to make sure that we are sampling different parts of the state space. And then otherwise, we're going to select from the greedy action from the current policy. Right? So most of the time, we'll take the greedy action that we think is a good policy of the type of actions that we want to take and states that we want to see, and with a small probability, we'll sample something random. Okay, so then we'll take this action, AT, and we'll observe the next reward and the next state, so RT and ST plus 1. And then we'll take this and we'll store this transition in our replay memory that we're building up. And then we're going to train the network a little bit. So we're going to do experience replay, and we'll take a sample of random mini batches of transitions that we have from the replay memory, and then we'll perform a gradient descent step on this. Right, so this is going to be our full training loop. We're going to be continuously playing this game, and then also sampling mini batches using experience replay to update our weights of our Q network, and then continuing in this fashion. Okay, so let's see if I can. Is this playing? Okay, so let's take a look at this deep Q learning algorithm from Google DeepMind, trained on Atari game of Breakout. Right, so it's saying here that our input is just going to be our state, our raw game pixels. And so here we're looking at what's happening at the beginning of training. So we've just started training a bit, and right, so it's going to look it's learned to kind of hit the ball, but it's not doing a very good job of sustaining this. But it is looking for the ball. Okay, so now after some more training, it looks like a couple hours. Okay, so now it's learning to do a pretty good job here. Right, so it's able to continuously follow this ball and be able to remove most of the blocks. Right. So now after 240 minutes. Okay, so here it's found the pro strategy, right? You want to get all the way to the top and then have it go by itself. Okay, so this is an example of using deep Q learning in order to train an agent to be able to play Atari games. It's able to do this on many Atari games, and so you can check out some more of this online. Okay, so we've talked about Q learning, but there is a problem with Q learning, right? It can be challenging, and what's the problem? Well, the problem can be that the Q function is very complicated, right? So we're saying that we want to learn the value of every state action pair. So if let's say you have something, for example, a robot wanting to grasp an object, right? You can have a really high dimensional state. You have, let's say you have all of your, even just joint positions and angles, right? And so learning the exact value of every state action pair that you have, right, can be really, really hard to do. But on the other hand, your policy can be much simpler, right? Like what you want this robot to do, maybe just to have this, simple motion of just closing your hand, right? Just move your fingers in this particular direction and keep going. And so that leads to the question of, can we just learn this policy directly, right? Is it possible maybe to just find the best policy from a collection of policies without trying to go through this process of estimating your Q value and then using that to infer your policy? So this is an approach so this is an approach that we're going to call policy gradients. And so formally, let's define a class of parameterized policies, right? Parameterized by weights theta. And so for each policy, let's define the value of the policy. So J, our value J, given parameter theta, is going to be our expected cumulative sum of future rewards that we care about. So the same reward that we've been using. And so our goal then, under this setup, is that we want to find an optimal policy, theta star, which is the maximum, right, argmax over theta of J of theta. So we want to find the policy parameters that gives our best expected reward. So how can we do this? Any ideas? Okay, well, what we can do is just gradient ascent on our policy parameters, right? We've learned that given some objective that we have, some parameters, we can just use gradient ascent in order to continuously improve our parameters. And so let's talk more specifically about how we can do this, which we're going to call here the reinforced algorithm. So mathematically, we can write out our expected future reward over trajectories. And so we're going to sample these trajectories of experience, right? Like, for example, episodes of gameplay that we talked about earlier, S0, A0, R0, S1, A1, R1, and so on, using some policy pi of theta, right? And then so for each trajectory, we can compute a reward for that trajectory. It's the cumulative reward that we got from following this trajectory. And then the value of a policy pi sub theta is going to be just the expected reward of these trajectories that we can get from following pi sub theta. So that's here, this expectation over trajectories that we can get, sampling trajectories from our policy. Okay, so we want to do gradient ascent, right? So let's differentiate this. Once we differentiate this, then we can just take gradient steps like normal. So the problem is now if we try and just differentiate this exactly, this is intractable, right? So the gradient of an expectation is problematic when p is dependent on theta here, because here we want to take this gradient of p of tau given theta, but this is going to be, we want to take this integral over tau, right? So this is intractable. However, we can use a trick here to get around this, and this trick is taking this gradient that we want of p. We can rewrite this by just multiplying this by 1, by multiplying top and bottom both by p of tau given theta, right? And then if we look at these terms that we have now here in the way that I've written this on the left and the right, this is actually going to be equivalent to p of tau times our gradient with respect to theta of log of p, right? Because the gradient of log of p is just going to be 1 over p times gradient of p. Okay, so if we then inject this back into our expression that we had earlier for this gradient, we can see that what this will actually look like, right? Because now we have a gradient of log p times our probabilities of all of these trajectories, and then taking this integral here over tau. This is now going to be an expectation over our trajectories tau. And so what we've done here is that we've taken a gradient of an expectation and we've transformed it into an expectation of gradients, right? And so now we can use sample trajectories that we can get in order to estimate our gradient. And so we do this using Monte Carlo sampling, and this is one of the core ideas of reinforce. Okay, so looking at this this expression that we want to compute, can we compute these quantities that we had here without knowing the transition probabilities? Right, so we have that P of tau is going to be, the probability of a trajectory is going to be the product of all of our transition probabilities of the next state that we get given our current state in action, as well as our probability of the actions that we've taken under our policy pi, right? So we're going to multiply all of these together and get our probability of our trajectory. So this log of P of tau that we want to compute is going to be, we just take this log, and this will separate this out into a sum of pushing the logs inside. And then here, when we differentiate this, we can see we want to differentiate with respect to theta. But this first term that we have here, log P of the state transition probabilities, there's no theta term here. And so the only place where we have theta is the second term that we have of log of pi sub theta of our action given our state. And so this is the only term that we keep in our gradient estimate. And so we can see here that this doesn't depend on the transition probabilities, right? So we actually don't need to know our transition probabilities in order to compute our gradient estimate. And then, so therefore, when we're sampling these, for any given trajectory tau, we can estimate J of theta using this gradient estimate. This is here shown for a single trajectory from what we had earlier. And then we can also sample over multiple trajectories to get the expectation. Okay, so given this gradient estimator that we've derived, the interpretation that we can make from this here is that if our reward for a trajectory is high, if the reward that we got from taking the sequence of actions was good, then let's push up the probabilities of all the actions that we've seen. Right? We're just gonna say that these were good actions that we took. And then if the reward is low, we want to push down these probabilities. We want to say these were bad actions, let's try and not sample these so much. Right? And so we can see that's what's happening here, where we have pi of A given S. This is the likelihood of the actions that we've taken. And then we're going to scale this. We're going to take the gradient, and the gradient is going to tell us how much should we change the parameters in order to increase our likelihood of our action A, right? And then we're going to take this and scale it by how much reward we actually got from this. So how good were these actions in reality? Okay, so this might seem simplistic to say that, you know, if a trajectory is good, then we're saying here all of its actions were good, right? But in expectation, this actually averages out. So we have an unbiased estimator here. And so if you have many samples of this, then we will get an accurate estimate of our gradient. And this is nice because we can just take gradient steps, and we know that we're going to be improving our loss function and in getting closer to at least some local optimum of our policy parameters theta. Right, but there is a problem with this, and the problem is that this also suffers from high variance, right? Because this credit assignment is really hard, right? We're saying that given our reward that we got, we're gonna say all of the actions were good. We're just gonna hope that this assignment of which actions were actually the best actions that mattered are going to average out over time, and so this is really hard, and we need a lot of samples in order to have a good estimate. Right, so this leads to the question of, is there anything that we can do to reduce the variance and improve the estimator?
다음은 케이스 스터디로서 아타리 게임을 플레이하는 것에 대해서 알아보겠습니다. 오브젝티브는 게임을 하이스코어로 끝마치는 것입니다. 스테이트는 게임의 스테이트를 나타내는 로우 픽셀 인풋입니다. 액션은 게임의 컨트롤러 레프트, 라이트, 업, 다운 등이 있습니다. 리워드는 각각의 타임 스텝에서 스코어가 증가하거나 감소하는 것입니다. 다음은 Q러닝에 사용할 Q 네트워크 아키텍처입니다. QSA 세타는 웨이트 세타를 가진 뉴럴 네트워크입니다. 인풋은 스테이트 ST로서 84 곱하기 84 곱하기 4의 디멘전을 갖는 지난 4개 프레임의 스택입니다. 이는 게임 화면을 RGB를 그레이스케일로 바꾸고 다운샘플링을 하고 크로핑하여 얻어질 수 있습니다. 인풋 레이어 위에는 우리에게 익숙한 컨볼루션 레이어들과 풀리 커넥티드 레이어들을 배치할 수 있습니다. 마지막 FC 레이어는 만약 4개의 액션이 있다면 그에 상응하는 4개의 아웃풋을 가질 수 있습니다. 즉, 각 액션마다 Q 밸류를 가지도록 합니다. 아타리 게임에서는 액션의 숫자가 게임에 따라서 4개에서 18개까지 변화할 수 있습니다. 이 방법의 장점은 싱글 포워드 패스를 통해서 모든 액션에 대한 Q 밸류들을 계산할 수 있다는 것입니다. 이것을 트레인하기 위해서는 이전에 배웠던 로스 펑션을 활용하면 됩니다. Q 네트워크를 트레이닝하는 데는 Experience Replay라는 방법이 사용될 수도 있습니다. 연속적인 샘플의 배치로부터 학습하는 것은 problematic, 문제를 발생할 수 있습니다. 그 이유는 샘플들이 correlate 돼서 러닝이 비효율적일 수 있기 때문입니다. 이를 위해서 Experience Replay를 사용할 수 있습니다. 기본적 아이디어는 트랜지션 테이블을 리플레이 메모리에 저장하고 계속해서 업데이트하는 것입니다. 이 메모리로부터 랜덤한 미니 배치를 샘플하여 Q 네트워크를 트레인하는 것입니다. Q 네트워크를 트레이닝해서 얻은 결과입니다. 여기까지는 다소 예상된 결과였지만 240분을 트레이닝한 뒤 놀라운 일이 나타나기 시작했습니다. Q 네트워크는 벽을 따라서 터널을 만드는 것이 가장 좋은 공략법이라는 것을 발견해내었습니다. 다음은 Policy Gradient에 대해서 알아보도록 하겠습니다. Q러닝은 문제를 갖고 있는데 Q 펑션이 매우 복잡해질 수 있다는 것입니다. 예를 들면 오브젝트를 쥐고 있는 로봇의 경우 매우 높은 차원의 스테이트를 갖고 있습니다. 따라서 모든 스테이트 액션 페어에 대해서 정확한 값을 학습하기가 어렵습니다. 하지만 policy는 훨씬 단순할 수 있습니다. 예를 들어서 close your hand 같은 policy를 선택할 수도 있습니다. 문제는 policy를 직접 학습하는 것입니다. 즉, policy들의 모음에서 best policy를 찾아내도록 하는 것입니다. 이를 해결하기 위해 policy gradient에 대해서 알아보겠습니다. 먼저 parameterized policy의 클래스는 pi로 정의됩니다. 여기서 pi는 weight theta에 의해서 parameterize 됩니다. 각각의 policy에서 j value는 미래의 리워드에 대한 cumulative sum의 기대값입니다. 우리의 목표는 optimal policy theta star를 찾는 것입니다. 이는 j theta를 맥시마이즈하는 theta 값을 찾는 것입니다. theta star는 policy 파라미터에 대한 gradient ascent를 통해서 찾을 수 있습니다. reinforce 알고리즘입니다. 수학적으로 우리는 j theta를 다음과 같이 표기할 수 있습니다. 여기서 r tau는 트로젝터리의 리워드입니다. 각각의 트로젝터리에서 우리는 리워드를 계산할 수 있습니다. j를 세타에 대한 그라디언트를 취하면 다음과 같은 식을 얻을 수 있습니다. j의 그라디언트를 바로 구하기는 어렵기 때문에 다음과 같은 트릭을 사용합니다. 이를 대입하면 j의 그라디언트를 구할 수 있는데 몬테칼로 샘플링으로 에스티메이트를 할 수 있습니다. 이 식이 가지는 의미는 expectation의 gradient는 구하기가 어렵기 때문에 gradient expectation으로 표현을 바꾼 것입니다. 다음은 trajectory의 확률을 transition 확률을 모를 때 계산할 수 있는지를 알아보겠습니다. 다음과 같이 P of tau는 트랜지션 확률과 펄러시의 곱으로 정의될 수 있습니다. 양변의 로그를 취하면 곱의 형태는 합의 형태로 변환됩니다. 양변에 세타의 그라디언트를 구하면 트랜지션 프로바빌리티는 세타에 의존하지 않기 때문에 그레디언트 값이 0이 되어서 식은 다음과 같이 정리됩니다. 이 식을 사용하여 J의 세타에 대한 그라디언트의 approximate 값을 구하도록 합니다.